Hi everyone, this video serves to go through the 2023 H2 Chem Promo Exam Paper 2, and we are starting with a definition question, which is to define the term relative isotopic mass. It is the ratio of the mass of an atom, of the isotope, to 1/12 the mass of a carbon-12 atom. If you put in the effort to memorize this, it should be an easy mark to score. Next, we move on to part 2. We give you a radioisotope, which is aluminium-28, and we describe beta decay as a process where we convert a neutron from a radioactive nucleus into a proton and an electron. So first, we note that the proton number of aluminium is 13, and the mass number or the nucleon number is given as 28, which tells us that this particular isotope has 15 neutrons and 13 electrons. So a neutron has been converted to a proton and an electron, which means that the number of neutrons has decreased by 1, while the number of protons and electrons has each increased by 1 after the process. So which means that after beta decay, this nucleus now has 14 protons, 14 electrons, as well as 14 neutrons. So from this, since the proton number of this nucleus is now 14, it is a silicon atom, and the mass number would be 14 plus 14, which is the number of protons plus number of neutrons, which is 28. So the symbol would be 2814 Si. Next, we have 1.000 grams of aluminium reacted with excess oxygen to form 1.906 grams of aluminium oxide. So this is the unbalanced equation. Al plus O2 gives Al2O3. We are going to balance the oxygens first. We multiply by 3 on the reactants side and 2 on the products side, so that both sides now have 6 oxygens. And now we multiply by 4 on the reactants side of the Al, so that the Al both sides have 4. So with this, we will first define the AR of the aluminium sample to be X. So we will calculate the amount of Al and amount of Al2O3 formed in the experiment. So the amount of Al would be 1.000 divided by X, whereas the amount of Al2O3 would be the 1.906 divided by 2x plus 48. 2x plus 48 represents the relative formula mass for aluminium oxide. Now that we have this, we can then compare the stoichiometry. Based on the equation, it is 4:2, which is 2:1. So the amount of Al is twice the amount of aluminium oxide. So we form an equation in X, and we simplify. 1.812x equals 48. X would be 48 divided by 8. 1.812 gives us 26.5. Okay, part B, part 1. We want to write the electronic configurations for Al3+ and Cr3+. So Al has an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p1. When it loses 3 electrons to become Al3+, the electronic configuration will just be 1s2, 2s2, 2p6. Next, for Cr, this is the electronic configuration. Now, for the first row of transition metals, we will fill the 4s subshell first, followed by 3d. So most of the first row transition metals have 3d and 4s2 configuration, with the exception of chromium and copper. Chromium is 3d5 4s1, copper is 3d10 4s1. So if we remove 3 electrons from a chromium atom, it will become 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. Next, to suggest why chromium 3 ions and aluminium 3 ions have almost the same ionic radii. Now, when we are comparing ionic radii, we have two factors we need to consider. The first one is nuclear charge. Nuclear charge is determined by the number of protons in the ion. The second factor is shielding effect, which is determined by the number of inner electrons within the ion. So first thing, chromium 3 ion has more protons than aluminium 3 ion, which gives it a higher nuclear charge. However, chromium 3 ion also has more shells of electrons, which means that it has more inner electrons, so it also has a higher shielding effect than aluminium 3 ion. So both of these are higher for Cr3+ compared to Al3+, and the two factors will sort of offset each other, which means that both ions have a similar effective nuclear charge, with the attraction between nucleus and the valence electrons for both ions being very similar, which results in them having a very similar ionic radius. Part C, we have aluminium sulfide combusted in excess oxygen to produce aluminium oxide and acidic oxide of sulfur, SOX. Okay. First, we are required to write the balance equation. So this is the unbalanced equation with SOX being a gas and we don't know the value of X. So we'll balance the S first. My reactant side has 3S, so I'll put a 3 in front of the SOX to balance the S on the product side. After that, my product now has 3 plus 3X oxygen, which means that my reactants side will now have 3 plus 3x over 2 oxygen. So this will be my balanced equation in terms of X. And it is noted that after I combust a sample in excess oxygen, there is a volume contraction of 120 cm3. And when the resultant gas is passed through aqueous NaOH, there is a further contraction of 240 cm3. So first you must know that this volume contraction of 240 cm3 represents the volume of SOX formed in the experiment, because SOX is mentioned that it is acidic, so it reacts with the alkali sodium hydroxide. So we need to track the volume of gases before and after the reaction. So at first, the gases is only oxygen, and there are two sources or two users of the oxygen. The first volume of oxygen is used to burn or to react with the aluminium sulfide, and the remainder is excess. It is not involved in the reaction. Then after that, there is a contraction of 120 cm3, and then it forms 240 cm3 of SOX, and the excess oxygen is left over. So you notice that the excess oxygen is constant for both volumes of gases, which tells us that the volume of oxygen used to burn aluminium sulfide will just be your 240 cm3 of SOX added to 120 cm3 of contraction, which is 360 cm3 of oxygen used to burn aluminium sulfide. And next, we are going to compare the volume ratios via Avogadro's law. So the volume ratios of oxygen to SOX is 360 to 240, and we compare it to the equation. So 360 to 240 equals to 3 plus 3x over 2 is to 3. And we simplify the ratio, we will get 3 plus 3x equals to 4.5. So I solve for x equals to 2. Next, we move on to question S2. In part A, we have given you 3 equations which eventually lead to the formation of dinitrogen pentoxide, N2O5. For part 1, you are required to explain in terms of delta G why reaction 1 occurs in car engines. Now, the question has already given you two pieces of information which you need. First one, that the entropy change for reaction 1 is slightly positive. Secondly, for reaction 1, the enthalpy change is also positive. And if the question is asking you why the reaction occurs, it should be a hint that is asking you on the spontaneity of a reaction, so the delta G is less than 0. So to answer this question, you must quote the equation for delta G first. So delta G equals delta H minus T delta S. And using this equation, for delta G to be negative, you will need delta H to be less positive than T delta S. And this is possible because car engines operate at a high temperature. So when the T is high, your T delta S term becomes much more positive than your delta H. So even though delta H is positive, your delta H minus T delta S becomes negative at high temperatures, which makes the reaction spontaneous. Part 2, to write the equation which corresponds to the enthalpy change of formation of gaseous N2O5. This should be quite simple. You will just need to fix the product N2O5 as 1 mole, and the reactants are gaseous N2 and gaseous O2. You will use numbers and fractions to balance the reactants such that it forms 1 mole of N2O5. Also, don't forget to include your state symbols in your enthalpy change of formation equation. Part 3, using the data given to calculate the enthalpy change of formation of N2O5. So this is the equation that we have written in the previous part. So the left side, we are going to incorporate reactions 1, 2, and 3 and apply Hess law to calculate this enthalpy change. So this is the enthalpy change of formation of N2O5. So the first step, we are forming NO from N2 and O2. And after that, my NO is going to react with O2 to form NO2. And this step will be NO2 plus half O2. The last step will be to form N2O5. So I then substitute in the values. So formation of NO, enthalpy change plus 180. Formation of NO2 from NO, enthalpy change is negative 57. But because 2 moles of NO2 are formed, so I need to multiply negative 57 by 2. And finally, reaction 3, NO2 to N2O5, enthalpy change is negative 55. So I apply Hess law. The enthalpy change would be plus 180 plus 2 times negative 57 plus negative 55, which will give me positive 11 kilojoules per mole. Part 4, to draw dot and cross for N2O5. And a very big hint is given to you in the question to assume each molecule contains oxygen bonded to 2 nitrogen atoms, which is a hint to you that it contains an NON kind of structure. So the O atom, one of the O atoms will bridge the 2 nitrogen atoms, and there's 4 oxygens left over, which means that each nitrogen will be bonded to 2 other nitrogens. So just keep this in mind and make sure that all your atoms have a stable octet, and this is the dot and cross diagram you're going to get. So the nitrogens have 1 single bond, 1 dative bond, and 1 double bond to oxygen. This is how the Lewis structure looks like. Part B, formation of N2O5 in the car engines can be minimized by catalytic converter, and this is one of the reactions that occur inside. Part 1, explain why this is redox, using oxidation states. So obviously the first thing you have to do here is to calculate the oxidation states of every element in the substance in this equation. But if you're sharp enough, you should recognize that the only elements that change oxidation state are carbon and nitrogen. So first thing, you need to identify where is the reduction, where is the oxidation. So there is reduction because the OS, the oxidation state of nitrogen, decreases from +2 in NO to 0 in N2. Second thing, there is oxidation because the oxidation state of carbon increased from +2 in CO to +4 in CO2. So since reduction and oxidation have occurred at the same time, this is a redox reaction. Part 2. To write a balanced half equation to form nitrogen gas from nitrogen monoxide in the acidic medium. So what do we have here? We are going to start with NO and H plus as reactants because it's acidic medium, and the product is N2. So we're going to balance the N first. My reactants has 1, my product has 2 N's, so I'm going to put a 2 in front of NO for the reactants to balance the N. Next, we need to figure out the amount of electrons transferred in this reaction, and we have already found in part 1 that the oxidation state of nitrogen decreased from +2 to 0, which means that each nitrogen atom is actually going to gain 2 electrons. And with 2 nitrogens being in this equation, it means that there will be a total of 4 electrons being gained. So now that we have this, the last thing would just be to balance by adding the hydrogens and the water. So this will be your balanced half equation. To check whether this is valid or not, you can count the charges on both sides. So for example, my left side has 4 positive charges and 4 negative charges, which means that there is no charge on the reactants side. My product side also has no charges, so the charges are balanced on both sides, which makes this equation valid. Part 3, charge on electron is this value. Calculate the charge transferred to form 1 mole of nitrogen. So we note that when we form 1 mole of nitrogen, there is a 4 mole transfer of electrons needed. So the number of electrons would be 4 times Avogadro's number, which is 6.02 times 10 to the power of 23. And the total charge transfer would be this number of electrons multiplied by the charge of each electron, which will give you a total value of negative 38,500 coulombs. Part C on electronegativity. First part, to define what is electronegativity. So it is the ability of an atom, or the tendency of an atom in a covalent bond to attract the shared pair of electrons towards itself. So we know that the 3 most electronegative elements are fluorine, oxygen, and nitrogen. Across a period, electronegativity increases, and going up a group, electronegativity increases as well. Part 2, to calculate the difference in electronegativity between Cl and H. So formula is already given to you. You will just need to substitute in the various bond energy values that you can find in the data booklet. So HH bond energy is 436, ClCl is 244, HCl is 431. So you just substitute in each of these values into this given equation, and you will get 0.97 as the difference in electronegativity between both atoms or both elements. So part 3, to calculate the electronegativity value of chlorine. So we know that chlorine is more electronegative than hydrogen, which means that its electronegativity value is higher than hydrogen. Since hydrogen's electronegativity is 2.20, we are going to add the difference between Cl and H to 2.20. So the electronegativity for chlorine is 2.20 plus 0.97 will give you 3.17. Part D, there is a triangle which plots on the x-axis the average electronegativity, and XA minus XB is the y-axis. It plots the difference in electronegativity. So we're going to fill in part 1 first and then use our coordinates to plot on the diagram in figure 2.1. So first thing, okay, the x coordinate will be the average of the electronegativity values. So you just take the electronegativity values of Br and F, you add together, divide by 2 to find the average, which is 3.47. And the y coordinate will be the difference, which will be 3.98 minus 2.96, which is 1.02. So now that you have this, you can plot it on the graph. It will occupy this position on the graph. As long as your coordinate is plotted roughly correctly, you should get the mark. Part 2. Identify the compound in figure 2.1 with the greatest degree of ionic character. So we know that ionic bonding, there is a transfer of electrons from metal to non-metal. And for this transfer to be possible, there must be a very great difference in electronegativity between both elements. So for it to have the greatest degree of ionic character, the two elements must have a greatest difference in electronegativity. If you look at the diagram, this compound will be CsBr, cesium bromide, with the greatest difference in electronegativity. Finally, part 3. The boiling points of 3 compounds are given in this table to explain in terms of structure and bonding the difference in boiling points. So you need to account for 3 things in your answer for this question. First thing, you need to tell me the structure that these compounds have. Secondly, the types of forces of attraction that they have. And lastly, you need to link it to the energy to overcome the forces of attraction. So it's very obvious that all of these are covalent. They have simple molecular structures. And all of them have weak ID-ID interactions between molecules. Okay, you cannot use polarity or PD-PD interactions here, because if you use that, it will predict that CO has a higher boiling point than NO, but that is not the case. So the easiest way is to use the ID-ID interactions, and we know that ID-ID interactions strength is affected by the size of electron clouds. So you need to tell me that BRF is the biggest molecule, has the largest number of electrons, which can be polarized to form the strongest ID interactions. Or if you want to discuss in terms of CO being the smallest, it's also possible. And since BRF has the largest number of electrons and the strongest ID-ID interactions, the most energy is required to overcome the ID-ID interactions between BRF molecules to cause BRF to boil, which causes it to have the highest boiling point. Next, we move on to the essay questions, E1. We have vitamin C, which is a diprotic acid and dissociates twice. And we notice that Ka2 has a smaller value than Ka1. So part 1, asking you why this is so. So first thing, you note that if the Ka2 value is smaller than Ka1, it suggests to us that H2A is a stronger acid than Ha-, because the dissociation equilibrium for the first dissociation lies further to the right than for the second dissociation. So why is this the case? Because it is easier to remove a proton from a neutral molecule H2A than from Ha-. This is because when you try to remove a proton from Ha-, the negatively charged ion and the positively charged proton will attract each other. So you'll need additional energy to overcome this attraction, which makes it more difficult to remove the proton from Ha-. So because it's easier to remove the proton from H2A than from HA minus. The dissociation equilibrium for Ka1 lies further to the right, and this tells us that H2A is dissociated to a larger extent than HA minus. Part 2, calculate pKa1 of ascorbic acid. Now this is ABE. So when you see the small p, it just means negative log. So you're just going to substitute in this value of Ka1, and the pKa1 of ascorbic acid is 4.10. Part 3, to calculate the pH of 0.100 mole per dm cube ascorbic acid. So this is the equation, the shortcut equation that you can use. It is very easy. You just substitute in all the values. The H plus concentration is 2.83 times 10 to the power of negative 3 mole per dm cube. So pH is negative log of this, which will be 2.55 to 368. Part 4, we have already determined that 0.100 mole per dm cube of ascorbic acid has a H plus ion concentration of about 2.83 times 10 to the power of negative 3 mole per dm cube, which means that it is in this range of pH, which tells us that the color of the indicator will be yellow. Part 5 is titration curve, not in J1 syllabus. You will learn more about it in J2. Part B, what are the various roles of ammonia in the given equations? So now you need to know what do these mean and what do these various terms, acid, base, nucleophile, oxidizing agent, reducing agent, mean, and apply them to the given reactions. So first one, ammonia, it is a base, and more specifically it's a Bronsted-Lowry base, as it accepts a proton from water to form ammonium ion. Second one, it is a reducing agent. If you do the oxidation state calculations, you'll notice that ammonia, the nitrogen, has oxidation state of negative 3, N2 oxidation state is 0. So because it reduces HNO2 to N2, itself gets oxidized to N2 as well. So therefore it is a reducing agent. Part 3, NH3 plus NaH gives NaNH2 plus H2. In this one, it's an acid. So it has donated a proton to the H minus ion to form H2. And it itself, after losing the proton, it becomes NH2 minus ion. Part 4, this is again a redox reaction and is a reducing agent because it reduces the OCl minus ion to Cl minus. The oxidation state of chlorine decreases from +1 over here to -1 over here. Itself is oxidized from -3 in ammonia to -2 in hydrazine, N2H4. Lastly, part 5, this is a nucleophile. So we know that for ammonia, the N atom actually has a lone pair of electrons. It will use a lone pair of electrons to attack the partially positively charged carbon in this compound. Because the C atom is bonded to two very electronegative atoms, which are O and Cl, it bears a partial positive charge, which makes it able to be attacked by the NH3 as a nucleophile. Part C is a question on chem equilibrium. So part 1, what is the term dynamic equilibrium? This is a common definition question and it appeared in the review test as well. So there are 2 points that I must see in the answer. First point is about the rate of the forward and backward reaction in a reversible reaction, that both rates of forward and backward reaction are the same. Second point concerns the concentration of products and reactants, which is that the concentration of both products and reactants remain constant. Part 2, write the Kp expression for the reaction including units and calculate the partial pressure of Br2 at equilibrium. So This is the Kp expression. Please remember that I2 is a solid. Its concentration remains constant, so we do not include it in the Kp expression. So this is my Kp expression, and from here what I can do, question has given me Kp as 1.64, partial pressure of IBR as 0.80, so I will substitute in the values. So I will find the partial pressure of bromine as 0.390 atmospheres. Part 3, calculate the initial pressure of Br2 in the vessel. For this, I'm going to set up ice table and put in the values that I already know. So I know that the equilibrium partial pressure of bromine is 0.390. The equilibrium partial pressure of IBR is 0.80. And we let the initial pressure of bromine be X. We know that at equilibrium, there is no IBR present, which means that the initial partial pressure of IBR is 0. So from here, we can calculate the change in partial pressure of IBR as plus 0.80. And using this, we can calculate the change in partial pressure of Br2 as negative half of 0.80, which will be negative 0.40, which means that your initial partial pressure of bromine will just be your equilibrium pressure plus the change in pressure, which will be 0.790 atmospheres. Part 4, state and explain the effect on equilibrium yield of IBR when we add inert gas at constant pressure. Again, a question that has appeared in the review test before. So what do I need to see? First thing, if we add an inert gas but force the pressure to remain constant, it means that the container's volume must increase, and if it increases, what it means is that the partial pressures of all gaseous species will decrease. So, by Le Chatelier's principle, it will favor a reaction that produces more gaseous particles to make up for the decrease in pressure, to increase the pressure in the system. So therefore, in this equilibrium system, the forward reaction is favored because we are going from 1 mole to 2 moles of gases. The forward reaction is favored, the position of equilibrium will shift to the right, which means that you produce more IBR at equilibrium. Part 5, a question on Maxwell-Boltzmann distribution. So explain in terms of the Maxwell-Boltzmann distribution why increasing temperature increases the rate constant of a reaction. So this is how a standard Maxwell-Boltzmann distribution should look like. What we are looking out for a temperature Maxwell-Boltzmann distribution, I need to see two curves where one of them has a lower minimum and is more skewed to the right, and they are clearly labeled as T1 as T2. The graph with a lower minimum and skewed to the right has a higher temperature than the other graph. Second thing, you label the activation energy and you shade the proportion of molecules with kinetic energy greater than or equal to the activation energy at each temperature using different types of shading. You can shade one to the left and another to the right. Make sure that they appear different. Finally, you need a legend or a key explaining what your shading means. So in this diagram, shading to the left means that it represents a total proportion or number of particles with energy greater than or equal to EA at T2. And the vertical shading represents the total number of particles with energy greater than or equal to EA, activation energy at T1, where T2 is higher temperature than T1. So you cannot just stop here, you need some words to explain your diagram. So when the temperature is increased from T1 to T2, the proportion of reactant particles with kinetic energy greater than or equal to EA increases, which leads to an increase in the frequency of effective collisions. Thus, the rate of reaction increases. Correspondingly, the rate constant will increase. Finally, we move on to E2. For A part 1 and part 2, we have one bromobutane reacting under certain conditions to form alkene E. So part 1 and part 2 require you to state the type of reaction and the reagents and conditions. So this is elimination reaction. It takes place under alkali conditions, which is sodium hydroxide or potassium hydroxide in ethanol and heat. Next, two products are formed when E reacts with aqueous bromine. Why? Because this alkene E is asymmetrical, which means that we need to consider Markov-Nikolsky rule when we do electrophilic addition to this alkene. So, in the first step of electrophilic addition, your bromine electrophile is going to add to alkene E, and it can add either following Markov-Nikolsky rule or not following Markov-Nikolsky rule. If it adds following Markov-Nikolsky rule, that means the bromine will go on carbon 1, which means that the positive charge is on carbon 2, and this forms a secondary carbocation which is stabler because there are more alkyl groups bonded to the carbon bearing a positive charge, which will disperse the positive charge via the inductive effect. On the other hand, if we don't follow Markov-Nikolsky rule, that means that your bromine will add to carbon 2 and the positive charge lies on carbon 1. So from these intermediates, we are going to let the water nucleophile attack the carbon which bears a positive charge. So the major products will have a hydroxyl group on carbon 2 and a bromine atom on carbon 1. And my minor product will have hydroxyl group on carbon 1 and bromine on carbon 2. Next, part 4, we have F, which is an isomer of E. When F reacts with excess hot acidified KMnO4, we only form one organic product, which is G. So first thing, when alkenes react with hot acidified KMnO4, it is known as oxidative cleavage of the carbon-carbon double bond, and it can form either carboxylic acids or ketones as organic products, but carboxylic acids have 2 oxygen atoms, whereas ketones have 1 oxygen atom. So which makes it very obvious that G is actually a ketone. So G has this structure, and from here we can conclude that F has this structure, this part where in a double bond, one of the carbon atoms has 2 methyl groups attached to it. But we also note that F, being an isomer of E, has 4 carbons, but we only have 3 carbons accounted for, which means that the last carbon was lost as carbon dioxide. So it also tells us that F has a CH2 group, which means that F has this structure. Next, part B, we have alkanes with molecular formula C7H16 reacting with chlorine in UV light to give a monochloroisomers, with one of them having a chiral center. So alkanes reacting with chlorine in UV light is free radical substitution. So for free radical substitution, we know that it takes place in 3 stages. For the initiation, please use the half arrows to show how the bond undergoes homolytic fission to produce 2 chlorine radicals. Then propagation. For termination, it involves the collision of 2 radicals to form a neutral molecule. So there are 3 possible termination steps. To play safe, please show all the 3 termination steps. Next, to suggest the structures of H and I. Now this is similar to alkanes tutorial question 6. So if H forms a mixture of 3 monochloroisomers when it is subjected to free radical substitution, that means that there are 3 types of hydrogens in H which produce different isomers when substituted. So there are actually 2 possible structures of H. So this is the first possible identity of H. And the different types of H's are circled in different colors. And the product J has a chiral center, which means that it is substituted one of the black hydrogens to produce the compound with a chiral center indicated with an asterisk. The second structure of H is like this. So again, there are 3 types of hydrogens, and when you substitute any of the green hydrogens, it produces J with a chiral center. Next, finally, we have compound A with the following synthesis. So from to state the type of hybridization of the carbon, mark with an asterisk, and to show the arrangement of the hybrid orbitals of the carbon. So this is an alkene, right? Which means that with respect to this carbon, the shape is trigonal planar, 120 degrees. So it tells us that the hybridization is sp2. And this is how sp2 hybrid orbitals look like. Please make sure that your major lobes are 120 degrees apart, and please don't leave out the minor lobes of the orbitals in this hybrid orbital. Part 3, state the reagents and conditions used in step 1. So this compound A is an alcohol. After step 1, it becomes an alkene. So this is again elimination reaction, but different from the halogenoalkane elimination, this takes place under acidic conditions. So you can either say excess concentrated sulfuric acid with heat or aluminium oxide with heat. Part 4, state the type of stereoisomerism exhibited by C and explain how it arises. Draw and label the structures of stereoisomers. So C, if you notice, has a carbon-carbon double bond, and we observe that each carbon has 2 different groups attached to it. So which means that the type of stereoisomerism would be cis-trans. So this arises because in the carbon-carbon double bond, each carbon has 2 different groups attached to it, and it arises because the carbon-carbon double bond is rigid. There is restricted rotation about the carbon-carbon double bond, which makes your cis and trans actually distinct compounds. So if your 2 groups are opposite side, in this case your 2 H atoms are opposite, it will be trans. If your 2 H atoms are on the same side, it will be cis. Finally, the last part, step 1, use a mixture of compounds C and D. Suggest a structure for D. So this is your compound A. To form compound C, we will remove a H from this carbon as well as the OH from this carbon to form compound C, which is this. But we can also remove a H from this carbon and the OH from this carbon to form another alkene. So if we do elimination this way, it forms this alkene as a product. So this is the structure of D. Finally, we are moving on to D part 1. We have 0.100 mole of an alkene reacting with hydrogen gas. So first we need to use ideal gas equation to find the amount or the number of moles of hydrogen gas reacted. So this is the ideal gas equation. We're just going to substitute in all the numbers. P is 1.24 times 10 to the power of 5 pascals. V is 600 cm cubed. To convert to meters cubed, you multiply by 10 to the power of negative 6. And temperature is 298 kelvins. The ideal gas constant is 8.31. So you can simplify. The amount of hydrogen is 0.0300 moles. And you notice that this is 3 times the amount of liquid alkene that is present. So you can rationalize that since the alkene reacted with hydrogen gas in a 1:3 stoichiometry, it suggests that 1 molecule of alkene contains 3 CC double bonds. Part 2, we want to sketch a graph for how the density of an ideal gas varies with 1/T at P1 and P2, with P2 being greater than P1. So again, we are going to start with the ideal gas equation, but ideal gas equation does not contain density. So what we're going to do, question has already hinted to you that density is mass divided by volume. So I'm going to write the V in the ideal gas equation as mass over density. So this is rho, it stands for density. So P times m over rho equals nRT. After that, I multiply both sides by rho and I divide both sides by T to get P over Tm equals to nR times rho. So eventually, if I simplify, I will get rho equals to Pm over nR multiplied by 1/T. So this simplified form will allow us to plot a graph of rho over against 1/T, and you can see that the graph of density rho against 1/T is linear, where the gradient is Pm over nR. So it also tells us that the higher my pressure, the steeper the gradient of the graph. So if P2 is greater than P1, it means that my P2 graph has a steeper gradient than my P1 graph. So this is how my graphs look like.